In this lesson, we're going to learn about linked list. And linked list happens to be a very powerful data structure in programming. We'll learn the different types of linked list. We'll learn about the nodes and how they are connected using references. We'll learn the differences between a linked list and an array. Also, we'll learn how to perform basic operations on linked lists such as traversals, insertions, and deletion. And by the end of this lesson, you'll be able to implement and manipulate linked list. Most importantly, you'll be able to know when to use a linked list and how to use linked list to solve real-world problems. So, what is a linked list? A linked list is a type of data structure where each item is stored in its own container. This container is called a node. Each node holds two things: data and reference to the next node in the sequence. Unlike arrays where elements are stored in a continuous block of memory, in linked list, elements are scattered across memory with each node pointing to the next one. Because arrays are of fixed size, you can easily access any element based on its position, but when it comes to inserting or deleting items, especially in the middle, it can be very costly. Linked lists, on the other hand, have a flexible size. The size is not fixed. Elements are scattered across the memory. This way, it is easy to insert or remove items, especially at the beginning or in the middle. So let's get back to the linked list again. This is a typical structure of a linked list. Each node contains data, and this data here is 10, and it has a reference to the next node. So this node is linked to this one, which is the next node. The list starts with something called the head, which points to the first node. If the list is empty, the head is simply set to none. To access items in a linked list, we'll start from the head and follow the next until we get to the last node that is pointing to none. And this process is called traversing the list. So let's see it in action. We're going to be creating a simple node class, build a few nodes and link them together to form a basic linked list. So we'll start by creating the class node. So we'll have class node. And in this class, we'll start by stating our constructor, and we'll have self and we'll have data. And here we have self.data is equal to data. Then the next component of a node is next. Which node is it pointing to? So have self.next is equal to none. So with this, we've defined a basic node class. So let's go ahead and create a couple of nodes. And to do this, we're going to call this one node 1 is equal to node, and we'll put in a data. So let's have 10 here. Then we'll have node 2 is equal to node, and let's put 20 here. Then we have node 3 is equal to node, and we have 30 as our data. So what we're going to do now is we created 3 independent nodes. We want to link them together. So we want to link node 1 to node 2 and then link node 2 to node 3. And to do this, we'll simply write node 1.next is equal to node 2. Then we have node 2.next is equal to node 3. With this setup, node 1 is pointing to node 2, node 2 is pointing to node 3, and the next attribute of node 3 is pointing to none, because that is the default specification we'll have in our node class. So now I'm going to have print node 1.data to confirm whether the linking is working properly. And let's go ahead and run the code. And you can see node1.data is 10. So let's go ahead and print all the data for the remaining nodes. So we have print node2.data. We have print node3.data. And we'll run it. So you can see 10, 20, 30. So let's see which node node1 is pointing to. And to do that, we can simply do print node1.next.data. This is going to print the data for node 2 because node 1 is making reference to node 2. So we'll run it. You can see it is 20 because that is the data contained in node 2. But this is just a manual setup. To make things cleaner and easier to manage, we usually wrap the logic inside of a proper linked list class. But before we get into this, let's look at the different types of linked list. There are three main types of linked list. We'll have the singly linked list, we'll have the doubly linked list, and we have the circular linked list. Each one has its own structure and use cases. But let's start with the singly linked list. This is the simplest type, and here each node contains data and a reference to the next node. This way you can easily move in one direction from the head all the way to the tail, but you cannot move backwards. So we're going to start by creating a node class, and then we're going to be wrapping things up using the linked list class. Since we already created our node class, what we're going to do is to go ahead and create our linked list class. So I'm going to make some modification here. I'm going to remove all these things. So we have class linked list, and we have our constructor, and here we have self. Then we're going to specify an attribute, the head attribute. So have self.head is equal to none. When a linked list is empty, the head is none. So this is one thing you should keep in mind. So let's go ahead and look at some of the operations we can perform on a linked list, and then we'll get back and complete our linked list class. In a typical singly linked list, you can perform different types of operations. You can perform insertion, you can perform deletion, traversal, you can search for an element, you can make updates, you can determine the length, you can reverse a linked list. So let's go ahead and complete our linked list class and implement functionalities for performing these basic operations. So we're going to start with insertion. So we have insertion, and for insertion we can insert in different places. We can insert at the beginning, at the end, or anywhere else. But let's look at insertion at the beginning, and we'll call it insert at beginning. And here we're going to have self, and we have the value that we want to insert. Let's call this data. To insert at the beginning, what it means is that first you are going to start by creating a new node. So we have new node is equal to node. We're making use of the node class we've defined earlier. And inside the node, we'll pass in the data, which is this. Then the next thing we're going to do is that we want to assign the next attribute of this new node to the head of the linked list. And we're going to have new node dot next is equal to self dot head. Then we'll go ahead and then assign the self dot head to be the new node. So we'll have self dot head is equal to new node. So this is basically how you insert at the beginning. So let's go ahead and initialize this linked list and make some insertions. And to do this, we're going to have LL is equal to linked list. And here we're going to close the parenthesis. We'll go ahead and insert at the beginning. And to do that, I'm going to have LL dot insert at beginning. Then I'm going to be providing the data. So let me have 10. And with this, we're good. But we have to find a way to display the content of our linked list. And to do this, we're going to create a method called display. This display method is basically going through all the items contained in the list, starting from the head all the way to the end. So it's basically performing a traversal operation. So we have DEF display, and we have self to make it a proper method. We're going to be starting from the head. So we have our current node is equal to self.head. Then the next thing we're going to do is that we're going to be performing a loop. And because of the next attribute of each node, we're going to keep calling on the next attributes of each node until we get to the very end of the linked list. That is to the node that is pointing to none. And we have while current, while there is a node. And here we're going to have print. We want to print the data attribute of that node. So we have current dot data, and we want to put something like an arrow. So I'm going to use equality and greater than sign to represent an arrow. I want it to be in the same line, so I'm going to be making use of the end argument of the print function. So I'll have end is equal to this. Then I'll close my parenthesis. Then I'm going to call the next node. And to do this, I'm going to write current is equal to current dot next. So this is what will even trigger the loop. So for every loop, this current is equal to current.next is going to call on the next node. And this will continue until we get to none. And in a situation whereby there is no node in the linked list, we're going to print something like none, which means there is no node. And this is in the case of an empty linked list. So let's go ahead and print out what we have inserted in our linked list. So I'll go here and write ll.display, and I'll run the program, and you can see we have 10 and 10 is pointing to none. So we only have one item in this linked list. So let's go ahead and insert other values. And remember, we're inserting at the beginning. So if we're inserting the second one, this one is going to come before 10. So let me change this to 20 and we'll run it. You can see 20 came before 10. Then let's do another one, and this one is going to be 30, and 30 will come before 20. So this is for inserting at the beginning. Now we're going to insert at the end, and for this we're going to have insert at end. We have self and we have data. Then we're going to create a new node, and for this we have new node is equal to node, and we'll pass in the data. But before we go ahead and perform the insertion, we need to confirm whether we're dealing with an empty linked list. If we're dealing with an empty linked list, all we have to do is to assign the self.head to the new node. And we're going to have if self.head is none, which is an empty list. We'll have self.head is equal to new node. Then we'll return. that will be all. But if it is not an empty list, we're going to perform some traversal starting from the beginning of the list, which is the head, all the way to the end. And we're going to start by having current to be equal to self.head. Then we'll perform an iteration. So we'll have while current.next. And the reason why we're using current.next is that we want to get to that node that is pointing at none. And we have current is equal to current.next. This will keep on moving us to the next node until we get to the end of the linked list. And once we get to that point where the current.next is equal to none, the loop is going to terminate. Then we're now going to assign that current.next, which is currently pointing at none, to the new node. And once we do that, we'll performed insertion at the end. So have current.next is equal to new node. And with this, we can be able to insert at the end of a linked list. So let's go ahead and try this out. Currently, we have 30, 20, and 10. And we want to insert at the end, which means we're inserting after 10. So let's go ahead and have ll.insert at end. And we pass in a value. So let's use 100 and then run the program. So you can see that 100 was inserted at the end. Let's go ahead and then insert another one. So we'll have ll.insert at end. And this time around, we use 110 and run it. You can see we have 110 at the end. The next thing we're going to do is we want to insert at a specific position. Usually, linked list doesn't support indexing, but we can insert at any position by traversing the linked list. So let's go ahead and try it out. And for this, we're going to have def insert at position. And here we have self, we have the data, and we have the position or the index where we want to do the insertion. First, we're going to create a new node. And here we have new node is equal to node, and we pass in the data, then close the parentheses. But before we go ahead and perform the insertion, we need to check whether we're inserting at the beginning. If we're inserting at the beginning, that is at the position of 0, we simply use the logic for insert at the beginning. To verify whether we're inserting at the beginning, we can have if position is equal to 0. This is at the beginning. Then we're going to have new node dot next is equal to self.head. I'm using the same logic for inserting at the beginning. And then we have self.head is equal to new node, and we'll return. And that will be all. But if we're not inserting at the beginning, it means that we'll have to traverse to the point where we want to perform our insertion. And to keep track of this traversal, we're going to be using count. So we have count, which is equal to 0. So we'll start at the beginning. We'll have current is equal to self.head. So we'll go ahead and traverse. So we have while current is not none, and we'll have count is less than position. So we have current is equal to current.next. Then we increment the count. So this is count plus equal to 1. So if you look at this while loop, you will notice that we have current is equal to current.next. At the end of the loop, current is not the present node. It is pointing at the next node. So to take care of this, we're going to have -1. Then we'll go ahead to confirm that current is not known, because while current is not known at this point, this particular line is pointing at the next node, which you don't know whether it is known. So we'll go ahead and have if current is known, means we're trying to insert at an invalid position. So we're going to raise an index error. So here we have raise index error. And for the message, we can write position out of bounds. Then we'll close this. But if current is not known, then we can safely perform our insertions. Then we'll go ahead and write new node dot next is equal to current dot next. Current dot next, of course, should be pointing at the next node, because you want to put that node at that position. And for the current node, you want it to be pointing at the new node. So we have current dot next is equal to new node. And with this, we are done. So let's go ahead and insert at a position. And for this, we're going to have, currently we have 5 elements in this list. So let's have ll.insert at position. And we're going to have our data as 200, and then the position is going to be 2. So let's go ahead and run this, and you can see it is successful. So currently we have 6 elements here. So let's try to see if we can put an invalid index. So let's put 7 here, or 7, and run it, and we're going to have an index error. So we cannot insert at that position because the position is not available. But if we try to put it at, let's say 4, it is going to work. So the insertion was done at the position 4. Just like insertion, we can delete at the beginning, we can delete at the end, or any other position. So let's start from the beginning. So here we have def delete at beginning. So have ourselves, and then the next thing we're going to do is to confirm whether we're dealing with an empty list. If we're dealing with an empty list, we'll simply raise an exception. So we'll have if self.head is none, then we'll raise an exception. So this is raise exception, and for the message, we'll simply write empty list, and that settles it. But if it is not an empty list, we're going to locate the next node after the head and make it the head. So what we're going to do is self.head is equal to self.head.next. This way, we have disconnected the current head from the linked list, thereby removing it. So let's go ahead and try it out. And we're going to remove this. We don't need it for now. And I'm going to have ll.delete at beginning. So let's run it. And currently we have 30 at the beginning. So let's try this out. And 30 has been removed. So let's see whether we can remove 20, which is currently the first element. So have delete at the beginning and run it, and 20 has been removed. So this is how we remove elements from the beginning in a linked list. So let's go ahead and try out deleting at the end. So we'll have def delete at end. Just like deleting at the beginning, we'll have to confirm whether we're dealing with an empty list. So we have if self.head is none, then we'll raise an exception. And for the message, we're going to have empty list. Then the next thing we're going to do is to check whether the list contains one item. because if it's containing one item, all you have to do is to assign the head to none and you will do the deletion. So we're going to have if self.head.next is none, which means that it contains one element. You simply have self.head is equal to none. This way you are going to delete that element. Then you return. Then if it is not an empty list and not a single item or single element list, then we're going to perform traversal. So we'll start from the beginning. So we'll have current is equal to self.head. And we're going to move all the way to the end of the list and now delete the last element. So here we have while current dot next. So let's explain this a little. So let's say we have a list that contains 3, 4, and 5, and you want to delete the last item. And currently we're at this position, and we want to check whether this particular element has another element after it. If it doesn't have another element after it, what we simply need to do is that we'll now change the next reference in this particular one to none. So that is why we're targeting 2 ahead. So we're going to have current is equal to current.next. And this will continue as long as current.next is not none. When it becomes none, just like in this case, after 5 we have none. So in this condition, what we'll simply do is that we're going to target this one and then assign the next to none, thereby removing 5. So what we're going to do now is that we're going to have current.next, and current.next is pointing to the node before the very last one that is referencing to none, and then assign it to none. This way you have removed the last node. So let's try it out, and currently we have 110 as our last node. So let's go ahead and delete at the end. So have ll.delete at end, and we'll run it, and we've removed the 110. So this is how we'll remove from the end. Apart from removing at the beginning, at the end, you can also remove by position. And for this, we're going to have def delete at position. And we're going to be specifying the position where we want to do the deletion. So we have position here. So first, we'll have to confirm that we're not dealing with an empty list. I can simply copy these particular lines and paste it below. So we have this. Then the next thing we're going to do is that we want to check whether the index is a valid index. Of course, if the index is below 0, it's an invalid index. So we have if position is less than 0, then we're going to raise an index error. So we'll have raise index error, and we'll have invalid index. Then the next thing we're going to do is to check whether the position is 0, because if it is 0, it means we're deleting from the beginning, which is quite easy. So we'll now have if position is equal to 0, then we're going to be using the logic for deleting at the beginning to handle this case. So we'll have self.head is equal to self.head.next, then we'll return. But if it is not at the beginning, then we have to move from the beginning, which is the head, all the way to the position where we want to delete. And first, we're going to start with current is equal to self.head, and we're going to be using count to track position, and we'll assign it to 0. So we'll have while current and count is less than position minus 1, Then we have current is equal to current dot next. We increment the count. We have count plus equal to 1. But before we go ahead with deletion, if current is none and current dot next is none, we're going to have an index issue. So here we're going to have raise index error, and we'll say position out of bounds. So instead of pointing the current node to the next node, we'll point it to the node after the next node. So we'll have current dot next is equal to current dot next dot next, thereby removing at that position. So let's go ahead and try this out. And so far we have 3 items in this list. So we want to remove 100, which is index of 1. So we have ll.delete at position, and we'll specify the position, which is 1, and run it. And you can see we've removed 100. So this is how to remove elements based on position. Next, we're going to be implementing a functionality for determining the length or the number of elements in a linked list. And we're going to have it as length. So first, we're going to use count to track our traversals. So we'll have it as 0. Then we're starting from the beginning. So we'll have current is equal to self.head. Then we'll have while current. And we have current is equal to current dot next. We increment our count, so have count plus equal to 1. Then we're going to return the count. So this is return count. So let's go ahead and try it out. So let me remove all these deletions and run it. So far we have 1, 2, 3, 4, 5, 6. So there are 6 elements in this linked list. So let's see whether our length method is going to do that for us. So we have value is equal to ll dot length, and we'll print value and run the program. So we have 6, which is correct. Next, we're going to be implementing the search method. With this method, we can check whether a linked list contains a given value. So we'll have def search. And here we're going to be specifying the value that we're looking for. So start at the beginning. So we'll have current is equal to self.head. And what we want to do is, if we get to that value, we're going to return the index. So I can have position is equal to 0. So let's go ahead and have a while loop. So we'll have while current. And here, if the data for the current node is equal to the value, it means that we found a match. So we'll have if current dot data is equal to value, then we can simply return the position. So write return position. We'll call on the next node. So we'll have current is equal to current dot next, and we increment the position. So we'll have position plus equal to 1. And this continues until we get to the last node. And if no match is found, we're going to return -1. So we'll have return -1. So let's try it out. And here I'm going to have value is equal to ll.search, and I'm searching for 10. So let's put 10 here and print value. And I'm getting a syntax error here. I'm using assignments where I'm supposed to use comparison. So I'll go over here and put another equality and run the program again. And it returns 2, which is the position of 10. So let's go ahead and put 110. So I have 110 here and I run it and it returned 5, which is the position of 110. So this is how you can search for values in your linked list. Now we're going to see how we can reverse our linked list. And for this, we're going to be having a method reverse. So we have def reverse. Currently, we have none as the last value. So we want a situation whereby we can have none like this. Then after the none, we're going to have 30. Then we're going to put the other one, which is 20. 20 is going to be at the back of 30. And 10 is going to be at the back of 20. And we have 100. We have 200. And finally, we have 110. So ultimately, if we can do this, it means that we have succeeded in reversing the list. And for us to achieve this, we're going to have previous. This is going to be a pointer and we'll assign it to none. Because currently, if we're to reverse this list, the last value there is none. So we want to assign previous to none. And we have current is equal to self.head. Then we're going to be performing a loop. We'll have while current. And we'll start by next node is equal to current.next. Then we're going to be assigning current.next to the previous. So we'll have current.next is equal to previous. Then we're going to be assigning previous now to the current node, which is current. And finally, we're going to be flipping the current to become the next node. So we'll have current is equal to next node. And at the end of the whole thing, we're going to be assigning self.head to become previous. So this way we can be able to reverse our linked list. So let's go ahead and try it out. And here we're going to have, let me remove this and we'll have ll.reverse. Then we'll run the program. You can see that it has been reversed. Let me comment this out, or better still, let me display before the reverse so that I can be able to see what happened. So I have this here and I run the program. So you can see this is our original list and this is our reversed list. Next, we're going to be looking at the doubly linked list.